Welcome to this particular lecture, and this lecture is very important since we are going to talk about how to fabricate a MOSFET, right. From last several class I am telling you that we are learning a process and I will show you in one of the lecture how you can fabricate finally a MOSFET. MOSFET is nothing but your metal oxide semiconductor field effect transistors. So, if I want to fabricate a MOSFET, what should be my process, right? What should be my process to fabricate my MOSFET? In that particular case, I have to understand what is oxidation, what is thermal evaporation, right? What is lithography, and then only I can understand how the MOSFET can be fabricated, alright. So, we have already seen what are the steps for fabricating a device. Now, using these steps how we can fabricate a MOSFET, that is the today's class, and then we will see several type of MOSFETs, meaning enhancement type MOSFET, depletion type MOSFET, P channel MOSFET, N channel enhancement type MOSFET, P channel enhancement type MOSFET, same way P channel depletion type, P channel enhancement type. Also we will see very short description or details about the complementary metal oxide semiconductor field effect transistor, which is your CMOS, alright. So, this is a important part or important chunk of the course, and we will also see an application of the MOSFET in terms of current mirror, alright. So, I will divide this particular lecture into few modules, so that we do not get lost when we are going to understand what exactly the MOSFET fabrication is and how they are applied for different applications, alright. So, let us see the first slide which you can see on the screen, and that is your class number 8, which is the MOSFETs, alright. So, for understanding MOSFET, what I told you, we have to understand the process, we have to understand the process which is our thermal oxidation, which we already know, right, oxidation, then we need to know deposition, then we need to know photolithography, right. Now, these three things we need to know, and if you know, and when one more step if you want to understand is diffusion or ion implantation, okay. So, these are the 4 steps that you need to know if you want to understand how MOSFET is fabricated, okay. Now, oxidation, we have already seen 2 types of oxidation, correct. One is thermal, another one is plasma enhanced chemical vapor deposition, right. This using the oxidation we can grow silicon dioxide, deposition we have seen, right. One is physical vapor deposition, another one is chemical vapor deposition, right. In physical vapor deposition we have seen 3 types, one is thermal evaporation, second is E-beam evaporation, and third one is sputtering. Right. And in CVD we have seen 2 types, PECVD and LPCVD. In CVD we have seen 2 types, LPCVD, PECVD, right. Then we have seen photolithography, and then this is the process that we need to see, but we will not go in detail. Just understand that if diffusion is there, there is 2 process in diffusion. Process 1 is called pre-deposition, process 2 is called drive in, alright. Pre-deposition and drive in. Ion implantation is another process which is heavily used instead of diffusion, since we can dope the impurities in much more accurate way using this technique called ion implantation. Alright. Now, once you know this, let us see quickly the section of lithography. Yesterday what we have seen, or last lecture what we have seen, that if I use lithography, I can understand how to inspect the pattern of photoresist, I can inspect the pattern created by the photoresist using what? Photolithography, correct, using photolithography. Now, what if there is a metal? Then how can we process? That means that how can we pattern a metal? This is again very important step, because the next slide I am going to show you the MOSFET. So, let us see how we can pattern the metal that is deposited on the oxidized silicon substrate using photolithography. Once you know this, then we will move on to the actual MOSFET fabrication. Okay. So, you come back to the screen and what you will see. So, I am showing you how to pattern, P-A-T-T-E-R-N, pattern metal, alright. Let me write out clearly, metal, alright, pattern, how to pattern the metal. So, we have already seen this example, we have seen interdigitated electrodes, isn't it, right, in SU8 well, we have seen this example. We have also seen how to fabricate gas sensor, right, using MEMS technology, right. Now, let us see quickly how to design a metal. That is same thing like interdigitated electrodes. We will just see so that you can get a refresher, and you understand how the MOSFET is. When I show you the process flow for MOSFET, you understand the process flow. So, now we know that if we have a wafer, right, if we have a oxidized wafer, and if I have a metal on oxidized wafer, metal, silicon dioxide, silicon dioxide. If I want to pattern this metal, then first thing I will do is I will spin coat photoresist, right. Then you know what is the next step after spin coating. Step 1, spin coat photoresist. Step 2 is soft baking, right, soft bake, right, 90 degree 1 minute hot plate. Step 3 load mask. So, we will load the mask, right, mask of our desired pattern, and then what we will do? Next step is we will expose the wafer which is spin coated with photoresist, right. Next step will be 4th step, expose with UV light, right. So, we are exposing with UV light, right, UV. This is your mask, correct. So, if I do this, what is the next step? Next step is I will unload the mask and develop, right. Next step is unload the mask and develop my photoresist. Once I develop my photoresist, what will I have? since this is a positive photoresist and my mask is bright field mask, what will I have? The area which is not exposed, this red one on the mask, okay, that area in the photoresist will be stronger since it is a positive photoresist. Again, the area which is not exposed will be stronger when we are using positive photoresist. So, what will I see? Once I complete my development step, that is I develop my photoresist, what can I see? I will see that the photoresist in the area that was not exposed will be there, and the area which was exposed by UV light, which is this one or this one or this one or this one, right, photoresist will be etched, photoresist will be developed, photoresist will get developed. So, now you know that you have the photoresist. Now, what is the next step? We want to etch the metal, right, because the idea is to pattern the metal, So, next step would be, after developing, next step would be we will do hard bake. Hard bake is done at 120 degree, 1 minute, hot plate, correct, 120 degree, 1 minute, hot plate, hard baking. After that, what is the next step? Next step is to etch metal. That means, we will dip the wafer in metal etchant. We will dip the wafer in metal etchant. On dipping the wafer in metal etchant, what will happen? The metal below the photoresist, you see the photoresist is right over here, okay. You look at this, photoresist is right over here. The metal which is below the photoresist will not get etched, and the metal in the rest of the area will get etched, right. So, when I etch the metal which is protected by photoresist, this is the one, 1, 2, 3, the metal which is protected by photoresist. Where is photoresist? Photoresist is this boxes, alright. So, metal which is protected by my photoresist will not get etched, metal which is not protected by my photoresist will get etched. So, when I etch the metal, I will have this particular thing. What is the next step? Next step is, of course, whenever you do metal etching, after that you have to rinse it, right, you know that you have to rinse it in deionized water and then you have to dry it using nitrogen. Rinse it and dry it, this is always there, after every step you have to do it, not after every step. Let us say for photoresist you do not have to rinse dry, soft bake is okay, loading mask is okay, exposure is okay, developed. After developing you have to again rinse it, rinse with DI and then dry with N2, okay. Then you have to do hard bake, metal etch. After metal etching, whenever there is a chemical involved, you see there is developing PR, there is a chemical to develop PR. So, we have to rinse with water. When we have to etch the metal, again chemical is involved. So, we have to rinse it with DI and dry it with nitrogen. What is the next step? Next step is, we do not want this photoresist, right, we do not want this photoresist. So, we have to strip the photoresist, we have to strip the photoresist. For stripping the photoresist, we all know we will dip our wafer, dip the wafer in acetone, dip the wafer in acetone. What will happen when we dip the wafer in acetone? You will see that the photoresist will be stripped off, Again you see what is there? Acetone. That means you have to again rinse. After acetone you have to rinse, okay, rinse with Di and dry with N2, dry with N2. Got it? Now how you can pattern the metal, you can, you know it, very easy, right, very easy, super easy. Oxidation you know it, metal deposition you know it, lithography you know it. This is an example of how we can do a photolithography using or for patterning the metal. Very important, because now we are going to the most important point of this particular course, and that is your MOSFET, and we will see how the MOSFET is fabricated. Alright. So, let us first see how MOSFET looks like in terms of schematic diagram. Okay. So, if I go on the next slide, you see, if you see on the next slide the MOSFET, what you see? You see that on the left side, just look at this MOSFET, okay, just look at this slide. What we see? There is a p type substrate, substrate is p type, means silicon we have taken which is p type. I have shown you types of silicon, right, I have shown you which type. There is a n type and there is p type, right. When I say types of silicon I have shown you, that means that I have shown you 100, 111 oriented wafers, right, in the previous lectures, 100, 111 orientation of the crystal, right, and then it was p and n, p and n. We can identify whether it is p type 100 or n type 100 or p type 111 or n type 111 based on the orientation or based on the primary flat and secondary flat, right. We are talking about primary flat and secondary flat. So, if you do not recall, you can go back to that lecture, look at how the primary flat and secondary flat helps us to understand whether the wafer is p type or the wafer is n type, and whether the orientation is 100 or the orientation is 111. Okay. All right. Now let us see this particular figure. This particular figure, what we see? There is a p type substrate. Okay. Then there is a n type. You see here, source, n type, diffusion, right. This is a source and drain. So, n type diffusion is done to form source and to form drain, right. N type is what? In p type I am what I am doing? I am doping my impurity which is n type, right. So, that this is my n type source and drain. After that I have a metal oxide, you see here, this is my metal oxide, right, and this metal oxide is nothing but my gate oxide, right. Then I have a metal here, you can see the metal here, this is metal, this is my metal oxide which is SiO2, this is my metal, right, because we need to connect it to metal to take out the external connection. This is my metal, you see, metal. Okay. I am just showing the schematic, do not worry, we will come back to the process flow where we will see each step in detail. Just look at the schematic, so we know how the MOSFET looks like, alright, how the MOSFET looks like. Now, I can apply potential difference or voltage between drain and source, So, here what I have done, I have applied positive voltage to the drain, positive to drain, negative to source, right. And if that is the case, what will happen? My electrons from here, right, it will get attracted towards the drain, my electrons will get attracted towards the drain, and we know that when this happens we can show the drain current in this particular direction, right. Drain current would be in this direction. Electrons are attracted from the negative which is source to the positive which is drain, right, because electrons are negative charge. So, it will go to positive terminal, and that positive terminal is my drain because my VDS is applied in this particular fashion. Next is, now you see here, what is this? This is my gate to source voltage, this is my gate to source voltage, right. So, what I have done? Here I have applied positive to gate and I have applied negative to source. Positive to gate and negative to source. That means the positive voltage here will cause the electrons from YP type to go towards the gate, right, which is a minority carrier. P type substrate is there, the minority carriers are electrons, majority carriers are holes, right. So, the minority carrier which are electrons will get attracted towards the gate because gate is positive, right. Since this will get attracted towards the gate, this electrons will form a n type channel which is written over here, right, which is written over here. You see, this is what is given. So, any schematic whenever you see, even it looks complex, in reality when we understand it is not complex. Okay. Now, what we see is electrons are attracted from p type towards the gate and it forms a channel which will be our n type channel, Okay. Now, when we have n type channel, with the help of channel only the electrons can flow, If there is no channel, how can electron flow from here to here? Not possible, right, not possible if there is no channel, right. So, if there is a channel, electrons will start flowing towards the drain, right. So, what does that mean? See, I will give you another example, okay, easy example. Suppose there is a there are lot of people on this island, okay, lot of people on this island. You see, these are two islands, okay, island number 1, island number 2. There are a lot of people on this island, lot of people on this island, and they want to reach to this island. So, island 1 they want to go to this particular island, alright. Now, what we see is there is a river, in between two islands, So, and the river is very deep and it is a long river. So, if the people try to cross, they do not know how to swim. So, they all will die, Now, in this case, if I have a bridge, right, connected between these two islands, then what will happen? The persons can cross this bridge from this island to the next island, right, from island 1 to island 2, correct. But what if there is no bridge? If there is no bridge, then they cannot cross the island, correct. Same way, if there is no bridge between source and drain, if there is no channel between source and drain, here is a source, here is a drain. If there is no channel between source and drain, electron cannot flow, cannot go from source to drain, even if I apply VDS. So, I have to create a channel and that channel is created with the help of gate to source voltage. Thus, this bridge is created so that the electron can flow from here to here. Also, this bridge is not only made of just for facilitating the electron to flow, but it is also made up of electrons. The bridge is also made up of electrons, right. So, these are all electrons lying in this fashion, so that now when I apply a source to drain voltage which is positive towards source, negative towards drain, then the electrons will flow from source to drain and the current will flow in the reverse direction, which is shown by the blue arrow. Alright, easy, understood, very clear, right. One thing what we see is, since you see there is a P and there is a N, right, this is a N, this is a P. So, there is a depletion layer, this is a depletion layer that is created, right. That is why it is shown here as depletion layer. When you have seen p-n junction, right? When you have seen p-n junction diode, you see that there is a depletion layer in the p-n junction diode. Alright, cool, easy. Now, one more thing is, let me just remove all these things so that we can see the schematic clearly, and I have taken this schematic diagram from electronics tutorials, which is right over here, so that you can understand. It was a good schematic, so I have used it for teaching you guys. Okay. Now, what is the next step? Next step is you see here there is a connection between source and the substrate. There is connection between source and substrate, right. So, you will see that the MOSFET generally, when you see, there are only 3 terminals: source, gate and drain. Source, gate and drain, right. So, why there is no 4th terminal? Why 4th terminal is not there? Because substrate is internally connected, is internally connected to the source. My substrate is internally connected to my source. That is why you will find that there are only 3 terminals in most of the MOSFET ICs that you can get from the market. Alright, very easy, super easy, right. Let us go to the next figure which we have on the screen, and that is our n channel enhancement type MOSFET. N channel enhancement type MOSFET structure. This I have taken from circuitstoday.com. Here what we see? We again see that there is a p type substrate. You see, I will tell you a beauty of what is here and what is here in just 1 minute, or maybe like 4-5 minutes 4-5 minutes, because I had to explain this particular structure. What is the similarity between this one, and what is the similarity between this two one? Okay, this I say 1 and this I say 2. What is the similarity? I will tell you in 4-5 minutes. Let us see here. What is here? It is p type substrate, alright, and then we have n type. You see here, n type dopant. It is a source, it is a drain, right, and then we have here a dielectric material which is SiO2, this is written over here. Then we have a gate. This is just a representative diagram, right. There actually the gate oxide is extremely thin, this gate oxide is extremely thin. Then we have a metal contact from gate, we have metal contact from source, we have metal contact from drain, and then you can see this is nothing but your metallization layer, right. This is nothing but your metallization layer. So, this one, which is figure number 2, is nothing but similar to your figure number 1, right. Figure 2 is similar to figure 1. Here p type substrate, source drain of n, Now, we have not applied the voltage, we have not applied any voltage here, we have not applied VGS, see VGS is not applied. Then we have not applied anything between drain and source, VDS is not there, VGS is not there. That is why you cannot see any formation of channel. In this case, if I just apply VDS, then very minority carriers that too from here can be get. But anyway, the point is, until unless you apply VGS, do not get confused with this, just until and apply VGS and VDS both, in this particular case you will not see any change in current, that is your drain current ID. We will also see what is the relation between VGS and ID, VDS and ID, we will draw the characteristics, we derive everything. But right now the point is, now you should know how the enhancement type n channel MOSFET looks like in terms of at least schematic diagram. Now, in the next slide what we will see is how we can fabricate a MOSFET, how we can fabricate an enhancement type MOSFET. Okay. So, let us see the next slide. and you take 1 minute, completely 1 minute to understand what is there on the screen. Alright. Look at this structure in particular, this one, this is P type silicon. I will write it somewhere so that it is easy. P type silicon. What we are looking at? We are looking at N channel MOSFET fabrication. We are looking at N channel MOSFET fabrication. Okay. What is this one? The red one, the first one is P type silicon. The second one, blue one, is N type silicon. The gray one, like light gray, is your silicon dioxide. Green one is your photoresist. Dark gray one is your metal. In this case, we have considered aluminum. You got it? What is that? Red one is P type silicon, blue one is N type silicon, light gray is silicon dioxide, green is photoresist, dark gray is metal. Okay. This much is there. Now, this one is side view, side view, side view, side view. Okay. You see the 4 one, I am writing SW so that I can understand. Side view, side view, side view, side view, or you can say cross sectional view, cross sectional view. This one is top view, top view, this one. Okay. This one is top view, this one is top view, my arrows, this one is top view and this one is top view. Okay. This one I am putting a right mark. Okay. These 4 are top view. We have side view, we had top view. Now, look at it and try to understand what is going on in this process flow. I give you 10 seconds to see, 10 seconds would be too less. Let us, I will give you 20 seconds to understand what exactly you understand with this particular process flow. You have to just see the side view or you can see the top view and guess what is going on, and then we will discuss one by one what is actually happening. Alright. 20 seconds starts now. Let us see whether you can understand or not. Okay, time's up. Less time, right? Less time to understand. Okay. So, let us see together. Okay. Let us see together what is given here and we will see that you will understand the complete process flow. Okay. So, start one by one, very easy. First step is you are taking a silicon wafer. What kind of silicon wafer? Red color is there. So, P type silicon wafer you have chosen. We have chosen P type silicon wafer. Next step is we have grown silicon dioxide, correct. We have grown silicon dioxide is written here, right, gray color, light gray. Next step is we have spin coated photoresist, correct, easy. Next step is we have performed photolithography and created a window. That means, we have etched the photoresist from this two area. We have etched the photoresist from this two window area, correct. You understood, right? See, first step is silicon, next step is silicon dioxide. We have grown silicon dioxide. Next step we have spin coated photoresist. After spin coating photoresist, we have opened this window using photolithography. You already know how to do that. I have shown it to you in previous examples. Once you create a window, the next step would be to etch the, we have to etch the silicon dioxide. So, here we have etched silicon dioxide. So, you can see here silicon, right. What you can see here is silicon. What you can see here is silicon, right, here and here. Why? Because we have etched the silicon dioxide. How we can etch the silicon dioxide? I have told you, we can use buffer hydrofluoric acid, buffer hydrofluoric acid, right. Until here is okay, easy. Let us repeat only this section. Okay. See, first step is we take a p type silicon. Next step is we grow silicon dioxide, right. How we grow silicon dioxide? By using thermal oxidation. Okay. Next step is we spin coat photoresist. After spin coating photoresist, we have to do pre baking, right, or soft baking. Then we have to load the mask, and then we have to expose the wafer. Then we have to develop the photoresist, and when you develop the photoresist, because your patterns are such that you will etch the photoresist from these two windows, this one and this one, you can see here, right, gray color, light gray. What does that mean? That you can see silicon dioxide below the photoresist. So, rest of the area of the wafer is protected by photoresist. The area which is shown by these arrows, these two arrow, right, it is not protected by the photoresist. Now, I will dip this wafer into the buffer hydrofluoric acid. On dipping this wafer in buffer hydrofluoric acid, what will I have? I will etch the silicon dioxide. When I etch silicon dioxide, what I can see? I can see if I remove the silicon dioxide from here, what I can see? I can see silicon, right. That is what I am looking here. I can see silicon when I etch the silicon dioxide. Now, it is easy. This much easy. The what we have done? We have created two windows. We have created two windows, 1 and 2, right, on the oxidized silicon substrate, such that I can see silicon through this window. What is the next step? Next step is that you have to remove the photoresist. For removing photoresist, very easy. What we can do? We can dip the wafer. We can dip this wafer into acetone. Photoresist removal, you know it, right. So, this is where we dip the wafer in acetone, and we can see there is only silicon dioxide. This is SiO2, and the red color is nothing but your silicon, p type silicon, right. So, we have reached until here. Next step is we have to diffuse, or we have to ion implant. What we have to ion implant or diffuse? We have to ion implant or diffuse n type silicon. N type silicon is this blue color. Okay. So, we have to diffuse or implant the n type silicon into the p type silicon. Why? So, that when we diffuse this and this, we are creating source and drain. We are creating source and drain. You can see here cross section. See, we are diffusing here. So, this silicon dioxide with the n type silicon, this is silicon dioxide, n type silicon, the dopant cannot penetrate through SiO2. Okay. The n type dopant cannot penetrate through SiO2, through silicon dioxide, and that is why we can say that silicon dioxide acts as a mask, protective mask, so that the dopant would not diffuse, but the dopants can diffuse in the window. Dopant can diffuse in the window. That is what we see here, that we can diffuse the dopant in the window created, and thus we have the source and drain, right, the diffusion of source and drain. This diffusion is n type diffusion. Why? Because we started with p type substrate. this is p type substrate, red one is p type substrate. So, we have to diffuse the dopant which is n type dopant, because we are creating an n channel, channel should be n channel MOSFET. Easy, easy, very easy, right. Let us see the next one. What is the next one? Next is we again grow silicon dioxide. Okay. You see, we have again grown silicon dioxide. So, you can see here, right. What is the next step? Next step is we have spin coated photoresist. We have spin coated photoresist. Next step is we have etched the photoresist from this particular area. This particular area is right over here, right over here, right. After this I have to etch the window, right. So, what is etch the window means that what you can see here, I can see here SiO2, I can see here SiO2, right. You can see here SiO2, see why, because there is a window created. So, once I see the SiO2, what will I do? I had to etch SiO2. So, when I etch SiO2, how can I etch SiO2? By dipping this wafer into buffer hydrofluoric acid, I will get this particular image. What you can see? You can see on the cross section, you can see the photoresist is there, the gate oxide is there, here gate oxide is there, here there is no oxide. You see in this region you see there is no oxide, So, we can directly see silicon. This is what you can see here, right. What you can see? That you can see there is a n type, in the center there is silicon, you can see silicon, correct, easy. So, after this what we have to do? After this we have to etch the PR or strip of the PR. Stripping of the PR is by dipping the wafer into acetone, correct. So, we are now dipping the wafer into acetone, we will get this particular wafer. So, what we have? We can have a silicon directly exposed here, right, and little bit of gate, a little bit of source, and drain areas are also exposed. You can see drain, source and silicon, three things you can see, right. So, now what we will do? Next step is we will grow a thin layer of oxide, where in this region, in this particular region we will grow a thin layer of oxide. So, because my pen is red you cannot see, but what I mean is this layer. So, you can see here, see thin layer of oxide we have grown. Why thin layer of oxide? Because this will be your gate oxide, correct. So, what we have done? We have grown a thin layer of oxide into this window, that is over the source and drain, such that it overlaps region of source and drain. So, what we have done? We have grown thin layer of oxide, which is our gate oxide. Okay. Until this is clear? Yes? Okay. No? Then you read once again. Okay. So, if you are with me, we have here which is our gate oxide. What is the next step? After gate oxide, we will spin coat photoresist. We will open the window, like this, such that the window goes all the way to the silicon dioxide, and in the next step we will etch this silicon dioxide. By using buffer hydrofluoric acid. So, you can see here, we can see now oxide, we can see here oxide, we can see here source, we can see here drain, right. So, what we can see here? We can directly see source and we can directly see drain, correct. So, where we see, come here at gate oxide. After creating a window, we created a gate oxide. After creating a gate oxide, we have spin coated photoresist. After spin coating photoresist, right, we have opened the window such that we can get the access to the source and drain. So, when you open the window you see silicon dioxide here, you can see silicon dioxide here. So, you have to etch the silicon dioxide. This silicon dioxide we can etch by placing the wafer in buffer hydrofluoric acid, and you can see source and drain. You can see source and drain right over here. Now, in this source and drain in this region, right, it is open, it is accessible. So, what we have to do? We have to grow a metal. We have to grow a metal because we have to take out the contact, external contact, right. So, for growing out the external contact, for taking out the external contact, we have to deposit aluminum or a metal. We have to deposit a metal. Now, once you deposit, what is the next step? Next step is you spin coat photoresist. Okay, spin coat photoresist, do lithography and open this particular area. Open this particular area. When you open this particular area, you can see here, this is the top view, this is a cross section. Then you etch the metal. You know how to etch the metal now, right. So, when you etch the metal, what you see here? There is a source connection for metal, there is a drain, metal is connected, and here is your gate, right. So, what you have done? You have now understood the process flow for n channel MOSFET. See, this is how the n channel MOSFET is fabricated, and here we now see that why we were understanding for hours what is, how can we grow thermal oxide, how can we deposit metal, how can we do lithography, why to do lithography, why to etch metal. Now, you can see why to learn all these steps before we can understand the process flow for fabricating n channel MOSFET. You got it, guys? You got it? It is not easy to get it. Okay. So, let me once again repeat it. Let me once again quickly repeat it, not in the same fashion, little bit faster, right, so that we can understand our MOSFET process flow. And if you observe, I will show you a trick. How many masks you have used? Here, right? Because you have etched, you have done lithography, you have again deposited metal, you have again done lithography, then you have doped the source and drain, right. Then you have created windows. So, how many masks you have used? 1 mask, 2 masks, 3 masks, or 4 masks? You know? You do not know, right? See how to find it. Okay, how to find it? Whenever we are depositing a photoresist, that will be 1 mask. You see, we are spin coating photoresist. So, not depositing, sorry, spin coating photoresist. Whenever we are spin coating photoresist, we will use 1 mask. See, photoresist spin coated 1, photoresist spin coated 2, photoresist spin coated 3rd time, photoresist spin coated 4th time, 4 mask process. Easy, right? Easy. What we will do generally when this kind of question is there, and if students are asked question, how many masks are used for fabricating a MOSFET, they will calculate, oh, this is first time I create a window, so maybe this is the first mask. Then when did I create a window? Somewhere, oh here there is second mask. Then oh here, is it one more mask? No, it is not one more mask. So, this is all confusion, right. You have to see so many steps to understand how many masks. A very easy way of understanding how many masks are used is just understand wherever spin coating of photoresist is done, you have to use a mask. Now, again thing is, this is because every time the pattern is different, right. That is why we are using 4 masks. For MOSFET, you can see very clearly 1, 2, 3, 4 masks. Okay. So, let us see what we have done here, starting with here. Okay. Concentrate, silicon, p type silicon we have taken, then we have grown silicon dioxide, right. On this silicon dioxide we have spin coated photoresist, After that we have done lithography technique. Whenever I say lithography, that means photolithography, it can be e beam lithography, which we it is not part of this particular course, but there are several types of lithography. One is photolithography, one is e beam lithography, then there is X-ray lithography, then there is a maskless lithography. Maskless lithography, we are not covering these things in this particular course, but you just understand that some lithography technique is used. Okay. So, anyway, so first step is silicon, which is p type silicon, then we have grown silicon dioxide, then we have spin coated photoresist, we have performed lithography, that means we have done soft baking, we have loaded the mask, we have exposed the wafer, we have developed the mask, and then we have reached to this particular section where we have created two windows. After creating window, we have to etch the silicon dioxide from this region. So, we are placing the wafer, this particular wafer into buffer hydrofluoric acid, and we will see this particular pattern, which is, you can see the silicon in the wafer. Now, you have to remove this photoresist. So, we have removed this photoresist by stripping it in by stripping the photoresist using acetone. After that, you have to dope this to area. So, we are using N type silicon to dope this to area, and we can dope it by using diffusion or ion implantation. Once we do this, we have source and drain. Now, we will grow silicon dioxide once again, we will spin coat photoresist. After spin coating photoresist, we will open a window which is in the center of the wafer, which in this particular fashion you can see here, and then we will etch the silicon dioxide. We will etch the silicon dioxide. You can see here we are etching, this is silicon dioxide already, and we have to etch the silicon dioxide. When we etch silicon dioxide, you will see this particular region where you can see source, drain, there is the N type diffusion layer, N type, right, N type, and you can see here in center there is a p type channel, right. So, this is what you see when you etch the SiO2, right, SiO2 was here, correct. So, when you etch SiO2 you reach to this particular region. After this, what you do, you remove the photoresist. Removing photoresist or stripping of photoresist is done in photoresist stripper, that is your acetone. When you do that, what you will obtain? You will obtain this particular wafer where your window is open, where you can grow the oxide. So, you have to grow thin layer of oxide, right, which is your gate oxide, Now, you know we have studied two types of oxidation in thermal oxidation. One is wet oxidation and another one is dry oxidation. And when I was teaching you wet oxidation and dry oxidation, I told you that when you have to use gate oxide, you have to use dry oxidation, and when you have to use filled oxide, you have to use wet oxidation. So, here for gate oxide we will use dry oxidation, and we will form a thin layer of gate oxide, which you can see right over here, right, or right over here in this particular cross section. We can see the gate oxide is here, and it is thinner compared to other oxide, which is here or here, right. This is thinner, which is gate oxide. Now, after growing gate oxide, we will again spin coat photoresist. We create a window, we remove the silicon dioxide, so that we can access the source and drain, After that, we will coat aluminum or a metal using, we will deposit, we will coat this wafer by depositing metal on this particular wafer. When we deposit the metal, you can see this, it is covering all the area, source, drain as well as gate. Then we have to you have to separate the source and gate and drain. That means source and gate should be separated, gate and drain should be separated. To do that, you have to again spin coat photoresist, do the lithography, and then you can see there is a separation. Then once the separation is there, you have to etch the metal from here, So, you have to dip this wafer in a aluminum etchant. When you do that, aluminum etchant, then you will see that the aluminum from rest of the area will get etched, right, and only you see here aluminum is etched, except at the source, at the drain and at the gate. You can see here source, drain and gate, correct. This is how you fabricate your N channel MOSFET. MOSFET. Alright, cool. So, this is how you fabricate your n channel MOSFET. So, look at all the lectures that I have taught you until now, and then only you will be able to understand how the n channel MOSFET can be fabricated. In a similar fashion, try to fabricate or try to draw the process flow, for the p channel MOSFET, right. Right now what I have shown you, an n channel MOSFET, and what I want you to do, what I want you to try at home is to draw the process flow for p channel MOSFET in the similar fashion. This is n channel, you see this is n channel. I want you to draw a p channel MOSFET. Is there a p channel MOSFET? If yes, draw it. If there is no, then do not draw it. Tell me whether it is possible or not. Okay? Try and let me know whether it is possible or not, whether we can understand, or we can write down the process flow of how to design or how to fabricate n channel and p channel MOSFETs. Alright. So, you know now that what is the use of our oxidation, you know now what is the use of our deposition, you know now how we are using photolithography, and how we are merging all the things together to understand how we can fabricate a MOSFET. In general, in quickly, what we understood today is how the MOSFET schematic looks like, what is the role of source, drain and gate, and we have taken example of a n channel MOSFET, right. We will see in the next module, which is part of the similar lecture, how we can understand the characteristics of the MOSFET, and how we can derive the drain to source VDS, that is voltage versus, or VD versus ID, or VDS versus ID, the drain characteristics for enhancement type, for depletion type, and we will also see the application of the MOSFET. Okay. So, I hope you understood what I have taught you today. Understand this, read this, listen to it. It is not so easy to grasp it at one time, even you know the things. So, just understand whatever I have taught you today, and if you have questions related to MOSFET or related to earlier lectures, now you are free to ask me any query. Alright. So, you can ask me query, I will get back to you with a proper solution, so that we are all on same page. Okay. So, till then you guys take care, and I will see you in the next module, where we understand the MOSFET in further details and understand how it can be operated. Okay. Till then you take care.